I actually just typed each of these scores into a different L column, all the way up to L5, to just keep it there, right? And then I figured out the range, mean standard deviation, and something should pop up. One thing, that the smallest standard deviation, right, of all the players resulted in the smallest range, right? If you look at all the ranges and compare all the standard deviations, Page had the smallest standard deviation and the smallest range. So very soon we're just going to focus on the mean and standard deviation, but I need you to see how they're related, right? We also saw that Morgan, right, had the greatest standard deviation and the greatest range as well. But Morgan also, I think there was a typo in the key. And if you did it, you know what I'm talking about. Morgan actually had the potential to score the highest of all and the lowest, which in the key it says 21, I think. I checked it. It was too late to change it. And it's actually 19. So highest and lowest for Morgan. So potential of scoring really high, but also potential of scoring really low. And that all over the place kind of scenario is what causes you to be inconsistent, right? You would call that you're inconsistent if you're scoring super high and then super low and then everything in between. Maybe you just had a bad day. Maybe Morgan got injured halfway through the game, right? We don't know. We don't know. Maybe just broke up, bad breakup, right? Couldn't play, couldn't focus. Who knows? Don't talk about that, Mr. Dixon. Anyways, so we have that, and when we look as a coach, you would say, okay, Paige is definitely the most consistent player. Morgan, not so much. And so as a coach, if you just look at these numbers, stats only, which player would you pick? For me, it would have been Patrice, actually. Because it has, if you compare all the averages, sure, it's not the highest average, right? You would say, well, this player Anna has a little slightly higher average, but Anna's more inconsistent. So everything in the mix, I would say Patrice has a fairly high average and a fairly low standard deviation, right? Those things combined make Patrice the most, I guess, the best pick in this scenario. Highest average means that on average you're scoring high, and not only that, being fairly consistent over all of the games, right? So those are the kinds of decisions that I need you to be able to make. Like, what does the mean tell me, and what does the standard deviation tell me? And maybe combining the two to pick out of a bunch of options. Maybe on a test, I'll just give you a bunch of scores. I won't ask you to actually calculate this, but I'll just say, hey, look at this. What can you tell me, right? Oh, I see that, this could be stores, right? Comparing stores and the amount of sales, right? Oh, this store sells more overall, looking at the average, but maybe it's not so consistent, right? Versus another store might be selling a little less, but it's more consistent. And so just be able to make those decisions. And so all these questions down here, I answered them on the key, right? So it's Google Classroom. They're actually typed up, and there's just that one typo there, right? The 21 instead of the 19. I'm saying that Morgan has the highest and the lowest of 21 for some reason. I must have looked at that, but it's really 48 and 19. That's the difference. Okay, so just wanted to briefly just cover it so that at least you've heard me talk about it, and to some degree. But I want to continue with the normal distribution curve. That's where we're going to park for a while now. So no, we're not going to forget how to graph. We're not going to forget how to do these. I'm actually having at least one more AC like the one I just returned to you, okay? There's at least one more coming your way like that. So be able to do graphs and figure out the mean, median, or all the MCTs given a frequency table. I looked at a bunch of your frequency tables when I asked you to figure out the mean and standard deviation. You did not find the midpoints, and so it wasn't the right, and you didn't do L1 and L2, right? So you didn't have the 540 or the 620 customers. So just learn from that, and moving forward, you know what to do, right? Find the midpoints, right? If there's a range like that, and you type it into two columns, and you need to feed both of them to one variable stats, right? If you don't feed the second column, it's going to think, it's really just going to think, oh, you're just considering these values here. If you type this into L1 and this into L2, it's saying, oh, this number shows up twice. This number shows up 5 times, right? 12 times and so forth. So you should have a total of 25 in this case, right? 25 employees. All right, normal distribution, we talked about it. We haven't completed it fully yet, so I need you to have the percentages. These are very important. We're going to actually make sure we have that on our study sheets. This is on page 13. And I want to add to this, along the x-axis, we normally will have what we call the data, right? So it could be height, comma, weight, could be volume, etc., right? It could be days, you name it. That will be along the x-axis. Right? So just consider, like, what kind of data are we collecting and how is it measured? And along the y-axis, you're going to have frequency, right? How often does that occur? And another note, how will I do this? I'm going to grab a different color and just really emphasize that curve. If you don't have it, it's not the biggest deal. Can't really see much anyways, but there's the curve. What's important to note is that this curve never touches the x-axis, okay? So I had to actually go in there and make sure I didn't make it touch, right? So never touches x-axis. So this curve never actually closes. And the reason being is that there's always a chance that there's some data way down this the curve way over to the right, and the same thing way over to the left. So we never actually touch the x-axis. There's also something that goes, so these would be the actual values that you've collected. There's also something called the z-scores. And it's not a German professor trying to say the scores, okay? It's not z-scores, right? Like it's z-scores, it means something in statistics, where the middle has a z-score of 0, and then 1, 2, 3 going to the right, -1, -2, -3 going to the left. And so the z-score essentially tells us how far from the mean we are, how many standard deviations from the mean would this particular height or weight be located, okay? Let's keep going here. You also need to remember these percentages within, like, the slices. We need to make sure we have that on our study sheet. Okay? So to summarize, the percent in each section represents the likelihood. So watch this. Okay? Percent in each section represents the likelihood or probability of data falling within the interval. That's very important to remember. Okay? So there's a 34% chance that if things are normally distributed, that it will fall between this value and that value along the x-axis. 34% chance that a value will be between these two upper and lower limits. And guys, these are going to end up being numbers, okay? So don't let that throw you off right now. We will do examples where this will make more sense, but this is how we come up with those numbers. Normal distribution follows a 68, 95, 99.7 rule. This rule is important because we're going to need that towards the end. A larger standard deviation results in a flatter curve. Flatter curve. Okay. Data is spread out. Okay. We are on page 13. Flatter curve, and a smaller standard deviation is a steeper curve. A steeper curve data is clustered around the mean. That's really, remember, standard deviation, it tells you the average distance of all the data points from the mean. That's what standard deviation does. It finds the average distance of every single data point that you've collected from the mean. So the greater that average distance, the further apart in general the data will be and farther from the mean, okay? The total area or probability under the curve is always 1 or 100%, okay? That's important to understand that, right? Under this bell curve, 100% of the data will be under it at some point, even if it's way down here, but it encompasses all of our data, right? There we go. Let's do some work with this, right? So now that we know a bunch of this stuff, remember that the average has 50% to the right above it, 50% is going to be below it, right? So let's go over to page 14. I'll give you some formulas there. Before I continue, I had actually at this point had a little bit of a, I hope it works. I had it loaded yesterday. I like to just use my iPad for this. But this is the average right here, mu, right, which is also known as the average. And this is my standard deviation, and it actually is a number right now. Look at what happens if I decrease my standard deviation. The curve actually, right, like the data points will be closer and closer to the mean. The mean is almost 4. Let's make it 4. Good luck, right? That's close enough, right? So the smaller the standard deviation, it means that the average distance of all points is getting smaller and smaller, right? So your curve is getting steeper and steeper. And if the standard deviation increases, it's telling us that the data points, because remember, there's a lot of points under the curve, right, that we've collected. Think of your line plot. Remember when things were doubling up, we would like put dots on top of it, right? Same idea here. But there's going to be fewer and fewer repetitions. It's going to be more spread out. So your curve gets flatter and flatter the bigger that standard deviation gets, right? So that's something to remember. And so I did say it in your notes that the standard deviation will tell you what the scale is along the x-axis, like how spread out it is. And your average, your mean, is going to determine where along the x-axis do you locate the data, right? So the bigger the average is, the higher up along the x-axis you will be. Now, this is not quite realistic because it could be hundreds or thousands, whatever we're collecting. Could be milliliters in a 2-liter bottle, right? And And so this will vary greatly, but I just want you to have a bit of a visual because it's so static in our notes, right? We think the curve always looks like that. It really doesn't. It could look like that, right? If we were to draw it to scale. And so keep that in mind. Not everything is normally distributed. Can we look at that real quick? I have some examples in your booklet. Let me see if I can find it. Or did I not add it? Oh yeah, here. Can you go to page 24 in your booklets? Page 24. I'm not going to talk a whole lot about it. I just want you to see some differences here. A normally distributed data set, when you graph it, should look symmetric. It won't be perfect. It won't be perfect, but you should see, okay, there's definitely a hat appearing here when I go over it. Whereas this one is off-centered, right? You would have a really big peak here, so you'd have a lot of data to the left, but it's off-centered. It's not symmetric when you look at this. And these are actually some of my former classes, right? They're the mark distribution from years before. I just grabbed two different classes, right? Or it could have been even one is a test, the other one is an AC, right? So, but not always is data normally distributed. Not always, okay? But we will talk about the ones that are for the moment, okay? Back to page 14. I can guarantee you that after we're done with this unit, you're going to hear some of these terms. And on the radio, maybe when you go to university, it's going to make sense to you because you've done stats in high school. Not a lot of students can graduate high school and say they understand stats, right? And stats is actually huge. Some of you are going to take a course in universities called stats, right? Statistics. And it gets tricky, but you'll have a background, right? Calculate z-scores by hand. When you are given the mean, I'm going to use mine. Right? When you're given the mean and the standard deviation, you can use the following formulas. Okay, so calculate the z-score would be like this. Z is x minus x bar over standard deviation. Okay? That's one of the formulas, and I'll just quickly tell you what everything is. That's your mean or average. Remember, it's the same thing. This is just the standard deviation. And this is the actual value. Make sure you copy that down and have this on your study sheet. On the right side, to calculate the value associated with a z-score. So I will put on top of this, just to make sure you understand, z-score is given. Right? If you will use this formula if z-score is actually given to you. And so I use this formula, by the way, guys. I just rewrite it. It'd be z times standard deviation plus the average. Z times standard deviation plus the average. And I would say this whole area here, I would box that in and make sure you have that on your study sheet. At this point, your study sheet can basically be completely filled in, both sides, right? By the time we're done with this unit, especially. The z-score tells us how many standard deviations, right? Highlight this. Z-score tells us how many standard deviations above or below the value is located. I should have said this. Above or below the mean, the value is located. So if your test score gives you a z-score of 1, that means that you're 1 standard deviation above the average. So you're actually doing good. If your z-score is -1 or -1.2, you will notice that the z-scores can be decimals. It's actually you're below the mean, right? So it's not a good scenario. So negative z-score, the value is below the mean. A positive z-score value is above the mean. Okay. Okay, let's do some actual work with this, okay, based on what we know right now. The height of males in Canada is found to be normally distributed. That's very important, right? That they tell you that. Then you can assume it's going to be a bell curve like this. The mean height is 177, and the standard deviation is 2.5. Graph a normal curve indicating the percentages within plus or minus 3 standard deviations, right? Include z-scores as well. Okay. So let's fill this in. I'm going to say I know that there's 68% here, 95% there. Soon you're going to have to make your own bell curve, but I thought for the first one, I'll just help you out here. Not drawn to scale, by the way. This is just filling in the percentages. We don't know how flat or steep this would be. Okay. And then average, this is your average right here. We know that our average is 177 centimeters. So you go here, be careful with, you need to write nice and small, okay? 177 centimeters. We're going to call this height in centimeters. Okay, I don't know why I put a bracket there. No bracket, just height in centimeters. That's what we're comparing along the x-axis. You grab your calculator because sometimes these numbers are ugly. I'll tell you that already. And you go 177. You're supposed to go 1 standard deviation up. So we're going to add our standard deviation, which is 2.5. That means that the value associated with this mark right here is 179.5. You got to write small. I apologize for that. Then you add another 2.5 to it because we're going to go another standard deviation to the right. And that is 182. Okay. And you keep going one more time. Another standard deviation, and that's 184.5. Make sure you understand this, guys. Can you just follow me? If you wanted to go from here straight to here, you go 177 plus how many standard deviations to get to here? 3, right? You would go plus 3 times 2.5. Thank you. Right? So I went 177, which is my average that was given to me. Right? And if you wanted to go straight to here, you just go plus 3 standard deviations. That's what I did here, 3 standard deviations. Boom. But it's easier to just go up by 1 every time because you need to fill this in. I'm going to ask you to do that. You do not need to, guys. This part here will soon not be required. I just have it there so you understand how we came up with those values. Let's go to the left. 177 minus 2.5. We're on page 14. This is 174.5. Take away another standard deviation. That's 172. Take away another standard deviation. It's 169.5. And there you have the values associated with every. So we are particularly concerned with one standard deviation width, guys. Do you understand that? It's equally spaced out along the bottom if you use a standard deviation. Could you keep going? Could you go a fourth standard deviation? You could, but remember, 3 standard deviations to either side from the average covers 99.7% of our data. So there's almost nothing expected out on the little edges here on the outskirts, right? We would consider those outliers, by the way. Okay. Let's put under frequency. This would be number of males, right? Number of males in this case. And let's fill in the sections. 34%, 34%. I split 68 in half, basically. Then, right, you're done with 68. This is 13.5 on either side. This is 2.35. Yeah, 2.35. So you gotta write really small. And if you need to put an arrow outside, that's fine. And then this little sliver here is 0.15%. And this little sliver here is 0.15% under the curve, right? And just for your notes here, I'm going to show you that what I did here is something happened from one number to the other, right? I went plus 2.5, plus 2.5, plus 2.5, and I went to the left, minus 2.5, minus 2.5, minus 2.5. That's how I came up with those numbers. Let me zoom in a little bit. You can do it, camera. There you go. This will soon be a lot less busy. Like we won't make it this crowded in a bit. Like this part right here that I've printed is not going to be there. Okay. And we're not going to tell ourselves that we're adding or subtracting, right? Can you, I'll let you copy this first. Make sure you have this down. Let's do a little experiment here. If I were to add this on the, you go all the way to this end and consider the value all the way on the other end. If I were to add these two and divide it by 2, I should technically get 177, right? That's the average. So let's try that. I'm going to have my 169. I'm going to clear my screen. 169.5, that's this value right here on the end, plus 184.5, which is way over on the other end. Enter, right? And then I divide that by 2. You get 177, right? It gives you the average because you're considering both ends. Same thing here. If you were to consider this value right here, 182 and 172, so 172 plus 182, and you divide that by 2, you still get 177. So if you're going out one standard deviation to either side, the average is still 177, right? So the average between the 2 points will always be the same. It's 177. And another thing I want you to understand is that given the fact that we were told that the heights of the males are normally distributed, we are expecting that 34% of males in Canada would have a height between 177 centimeters and 179.5 centimeters. Does that make sense? And so 2.35% would be expected to be between 182 and 184.5. And so where would Mr. Dirksen be on this curve? I'm 1.96 meters, so 196 centimeters. I would be like way down this curve, right? I don't even fit on in the belt, right? Like I'd be way down here somewhere. You got to understand that, right? And so if you're shorter, you're going to be, if this is the average and you're less than this, you're going to be somewhere here, right? And so you got to understand that. But most people, like, or not most, but 68% would fall between here and here. Right? 95% of people would be between 172 and 182. Where did you get 95 from? Well, right here at the top. Right, I go back 2 over 2, right? So that's 95% are within 2 standard deviations. So that's how you understand this curve. This is basically saying the chances that someone is between 174 and 177 is 34%. Chances that somebody's between -1 standard deviation and +1 standard deviation is 68%. Chances, that's a probability that we're saying. This is probability, okay? So it must add up to 100% when you're all said and done. Okay, let's answer this based on the graph here. What percentage of males are between 172 and 179? I will say this. For today, we answer based on graph. I will be very specific. I'll say either use your calculator or use the graph. If I make you graph something like this, base it on the graph. Do not base it on your calculator because soon we'll find out the exact amounts. These are not exact. They're a little bit off. Okay. What percentage of males are between this and this? So you go here. 172 is right here. Right? That's the first value. And 179.5 is right here. So you need to start here and add the percentages of each section, right? That gets you to this line right here. So everything in between is going to be, and I'm going to show my work here. Don't just give me the final answer, right? And that is 81.5% of males. Tomorrow, we're going to use our calculator. So I'm going to leave a little bit of space under here to figure out the exact amount. Okay? If you didn't, that's fine. We're going to squeeze it in. What percentage of males are expected to be, what happened there? Sorry, get rid of that P there. To be taller than 182 centimeters. Taller than this. So 82 is right here. You want everything taller than that. So you got to add these two here. 2.35% plus 0.15%. And that ends up being 2.5% of males. You can see that, right? Sorry again. So I basically just added everything past the 182 we went over. I forgot something on our graph. Z-scores. It's actually very easy to plot your Z-scores. Just have a heading Z-scores. So a height of 177 would put you right in the middle, which means that you have a Z-score of 0. Because remember, Z-score tells you how far above or below the mean you are. If you're right on 177, you are right on it. If you are at 179.5, you would be 1 standard deviation to the right, 2 standard deviations to the right, 3 standard deviations to the right. You go to the left, a height of 174.5 centimeters would place you 1 standard deviation to the left, 2 standard deviations to the left, 3 standard deviations to the left. Okay. And you have to ask yourself, Mr. Dixon, is it possible that something is in between here? Yes. Could somebody have a height of 178, which would put you somewhere in between? Yes, but we have to use our calculator for that. We cannot just base it on this graph. Okay? And it gets pretty cool because it will tell you exactly what it is. Let's go to D here, and we're still using our graph, right? I'm going to ask you to figure that one out. What percentage of males are shorter than 169.5 or taller than 179.5? Read it, try to figure it out. I'll just... So shorter than 169.5. Let's figure that out first. I'm going to do this. Shorter than that, so I'm going to go to my graph here. Shorter would be, if this is the height, you want everything less than that because it's shorter. So 0.15 is that part right here, 0.15%. Or you want this, or people that are taller than a certain height, which is 179.5. So where's 179.5? Is right here. So I need to add these three sections to figure out people that are taller, or percentages that are taller than that height. So I go 13.5 plus, I'm going to put that in brackets, 2.35 plus 1.5. Sorry, not right, 0.15. Okay. So I want to basically figure out, right, the combination, like people that are shorter than this height or taller than that height. So these percentages added up would take care of that. Shorter than, there's only a slight sliver there. So this ends up being 0.15 plus, this is 2.5, 16%, right? This adds up to 16%. So we have a total of 16.15% of males. Okay. It's trickier. I don't like where this is going, right? That's what you're thinking. You'll be fine. Is there another way of doing this part? There actually is. What we could have done is, follow me here to my graph. I could have, if I consider everybody shorter than this or taller than this, right? I could have actually figured out this part and taken that away from 100%, right? Because remember, the whole curve is 100%. So if you figure out what's in between those two values and take that away from 100%, you should arrive to the same conclusion. Okay? Exact same answer. So remember, you can use that to your advantage, knowing that the whole curve is 100%. You can sometimes take away. Okay? What is the range of heights for 99.7% of males? That number should actually mean a lot to you. This is telling you, let's put like a little, this is saying within, when you're at 99.7% of males, you're talking within 3 standard deviations. Right? Because remember, it's 68, 95, 99.7. So the range, right, would be all the way from 169.5 centimeters to, what's at the other extreme, 184.5 centimeters. Okay, let's say that 99.7%, right, would have a range of that. This would be the range. For 95% of males, what would that be for 95? We're talking 2 standard deviations, right? Remember, if you have your graph correctly, 95 gets you to, this is one standard deviation to either side, two standard deviations, sorry, there, two standard deviations to either side. So you go down and just copy those values. It's 172 and 182, right? It goes from 172 to 182. Those are the range of heights. And then 68 would be just one to either side. So you go and look it up. It's 174.5 centimeters to 179.5 centimeters. So that's what it's asking here when they're asking you the range of, could be height, weight, the range of days, you name it. Go ahead. Let's keep going here. If Canada has a male population of about, this is 17 million. Okay. I'm going to do the commas here to help us out. 17 million. Determine the number of males that are shorter than 172 centimeters. Okay. So I will say this. Find probability of being shorter than 172 centimeters first. Okay, find that first. Find the probability of being shorter than that. We use our graph. So that would be, if you go 172, right, we would have to add 2.35% and 0.15%, right? On my curve, I add everything to the left of 172, and that gives me 2.5%. Very important. I'm going to underline that. So therefore, right, I will take 17 million and multiply it by 0.025, which is 2.5% turned into a decimal. Does that make sense? Right? I divide it by 100 to get that, and then we'll just round our answer. If it doesn't round, then we need to round it, right? So 17 million times 0.025. So that's 425,000 males. I had to think here. And so the industry kind of uses this to make their decision when they design buses, when they design theaters, stadiums, stuff like that, right? The height of the dryers, like the hand dryers, right? Like how high, like what is the average height, what is most, right? So they do use this, the normal distribution curve, to figure out maybe the clothing industry, right? What should we make most of, right? Like what are the heights that we're gonna sell most of, and then they make less of everything else, right? That's why good luck for me finding shoes, right? If I go to, I don't even ask, ooh, I like this one. Do you have this one? I just ask them, do you have a size 13? Right? That's what I tell them. I don't care what it looks like. I just need shoes, right? And so they know this, right? It's not no news, but they do have to kind of cater it to their population, right? What percentage of males have heights with z-score between -2 and 1? What? Z-score? No problem. We have that in our normal curve, right? Um, Z-score, let's write this down. Z-score of -2 corresponds to a height of what the height will a z-score of -2 have? Look at your chart. That be 172 centimeters, correct? And a z-score of 1, a z-score of +1, right, corresponds to a height of 179.5. All from the graph, okay? So it's basically asking what percentage of males will be between these two heights. That's what it's basically asking, right? When it's saying the z-scores, it has a specific height associated with it. So we're gonna go and look it up. Have heights with a z-score between those two. So because of the wording, we're gonna say 13.5 plus 34 plus 34. And you're like, Mr. Dirksen, I know that's 68. Why can't I just go 68? Go for it. And that ends up being 81.5% of males. And basically what happened here, guys, just a little visual. If this is 0, then -1 and -2 is here, and +1 is here, right? And you notice that those are sections that we actually have, right? So this was 13.5, this is 34, and this is 34. So you basically just added the percentages associated in between those sections, and that's how we come up with this. Okay? So z-scores have a height associated with them. What is the range of heights that would have 95% of males comprised in it? We already did this. But 95%, right? This is saying plus or minus 2 standard deviations. Let's change the wording a little bit to make it quicker. When you see 95, you should say, oh yeah, it's 2 to the right and 2 to the left. Right? So that would be, if you look at it, it would be 172 centimeters to 182 centimeters. Doesn't hurt to do the same question again. The mean height of females is 162.5 with a standard deviation of 3. Sketch both curves on the same plane. How will they differ? Use different colors or patterns to illustrate the differences. This is where I take it up to the next level. Not really, but okay. Let's do this. Males. That'd be 177 centimeters average, standard deviation of 2.5 centimeters. Females, we are now told that the average is 162.5 centimeters. Standard deviation is 3 centimeters. Right there, you should be able to say this in a nutshell. In general, males are taller in general, and they're more consistently so. They're more consistently so. Females are in general shorter and not as consistent compared to males. Okay. I want you to not worry so much about the scale in this one. I just want you to show me how would they differ? Use the space beside because I have questions that I want to add underneath, okay? So this is what I'm going to do. I'm going to draw my x-axis, and this is going to be height in centimeters. We're going to do one at a time. But along this x-axis, males would be somewhere higher up, right? This is the average for males, and females are a bit shorter on average. This is Statistics Canada, by the way. You can go and look at this. I didn't make this up. Okay. So why am I focusing on the averages? Because that is the center of my curve, right? That's the middle. That's going to be the peak of the hat. So I'm going to use maybe, how about I use red for males and blue for females. If you want to go solid and dash, that's up to you. That's completely fine. Which of these curves is going to be steeper? Males or females? I don't know. Males, right? Remember, a smaller standard deviation, steeper curve, remember? So males will be slightly taller, like it will be higher up. And so that's where I focus on, and then I kind of just go like this from there. Try to make it as symmetric as possible. So we know that the male bell curve will be higher up along the x-axis, and the female will be lower. Right? So the mean tells you where along the x-axis will the bell curve be situated, and the standard deviation tells us flatter or steeper. So let's just make sure that the female curve is slightly flatter. Okay, slightly flatter than, and it's going to be lower as well. Lower, flatter, you name it. But if you graph them both on the same axes, right, it should make sense. This here means steeper. Because it has a lower standard deviation. I hope this makes sense. This is just sketching. I'm not asking to make a detailed scale diagram. This is just like, hey, if I asked you to sketch them, I should be able to see the differences. I should be able to cover this up and be able to say, okay, let's see here. The red is males, obviously that would have to be given. I'd be like, yeah, in general they're taller because their average, which is the peak of the curve, tells you that is higher. So in general, taller, and also because the curve is a little bit steeper, the standard deviation will be lower, right? Because you're more clustered around the mean, slightly more so than females, right? So you got to make sure you understand that. And practice will take care of this, of the concepts involved here. It's practice. That's all it's comes down to. I would like to add a question here, very important actually. Calculate the z-score of a male with a height of 181 centimeters. Calculate the z-score of a male with a height of 181 centimeters. Does 181 even show up on our graph? Look at your graph. Does it show up there? Doesn't. You can't guess, guys. You have to actually calculate. So if this had been 182, right? 182 is on your graph. So you could have just said what? The z-score is 2. But it's not. So you use this formula. Z-score is value minus average divided by standard deviation. So the z-score is, what's the actual value considered right now? It's 181 minus the average, which is 177, over the standard deviation, which is 2.5. You got to be careful here. Don't rush, okay? So you got to go 181 minus 177 first, which is 4. 4 divided by 2.5, and then you get your answer there, which is 1.6. No units, okay? Z-score does not have a unit, or does not have units attached to it at all. Does it make sense that it's 1.6 though? If you look at your graph, let's go and check it out. 1.6 would be right about there, which is close to 182, right? So it does make sense that it's 1.6, and it can be a decimal. Don't be scared of that, okay? It's saying that it's 1.6 standard deviations above the average, right? Therefore, 1.6 standard deviations above the mean. So if you have a height of 182 and your your z-score is 1.6, that means that you're taller than the average. If your z-score had been negative 1.6, which will happen, that means that you're shorter than the average in this particular scenario. Okay. Z-score of a height of 176 centimeters. What is the z-score of a height that is 176? Without doing the math, is this going to be positive or negative? It's going to be negative, right? Because 177 is our average. This is just slightly shorter than that. Let's do it. 176 minus 177 divided by 2.5. That's negative 1 over 2.5. That is negative 0.4. Therefore, 0.4 standard deviations below the mean. I go 0.4 standard deviations below the mean because of that. And this, if you ever take university and you take statistics, you're gonna have a leg up on everybody else, because these are the kinds of things that you're gonna need to know. And sometimes you need to take statistics for certain, like University 1, you take a bunch of random courses, statistics might be one of them. Okay. Don't ask me if I remember anything, but there was this kind of stuff for sure. Z-score, standard deviation, normal distribution, all of that will be for sure talked about there. Okay, your homework is right here, but this is textbook. I always make changes to this book. So let me just peek, because my version will differ from yours. I'm just going to peek on the next page if I added something. Maybe I added something that goes right with this. Let me just check. Yeah, yeah. You can, I would say, do this first, and then textbook. Okay. So I will say homework. I want you to make a graph. Okay, graph a normal distribution showing the probabilities for plus or minus 3 standard deviations, and include the z-scores, and then answer everything up below it based on your graph. You can bet that I will ask you to do that tomorrow. Okay, so your study sheet, I will post the key to this as well. Your study sheet should have enough information to allow you to fill in something like this, to know the 3 percentages, and from there be able to fill in every section like this. Okay, it's not that much to add. Like, you just make sure you put that on your study sheet, and these two formulas, right, that we also covered. Make sure you have that as well. How to calculate the z-score. You can, if you're given a z-score, you can actually find the height, the actual height. You can go backwards. I didn't do that today, but I will show you how to do that tomorrow and the days to come. Okay. Oh, we still have time to spare, so you maybe can. Why don't you start with your graph already on this one, and maybe just maybe you can do almost all of it in class. That's it, guys.